Okay, welcome to a short screencast dealing with the thought process involved in solving a couple of questions in the Reactions and Stoichiometry Unit Assessment. And just note, the thought process involved in these questions can actually apply to lots and lots of other questions involving chemical reactions and their stoichiometry. So let's get started. The first question is one of the versions of question 5. Many of these questions have different versions, so this one happens to deal with nitroglycerin and dynamite. Other versions of the question deal with different kinds of explosives, but the thought process is very similar. So first of all, we take a look at the question to see, get a sense of what information we have and what we're trying to find. So we have the formula for nitroglycerin. We are told that dynamite is made of nitroglycerin with some other stuff, some stabilizers and absorbents. And here is the reaction that nitroglycerin undergoes. And then we have some information about this particular problem. We have 40% dynamite, we have a length, a diameter, a mass. We're told it's 40% nitroglycerin by mass. And then the question is, what is the total number of moles of gas? So I'm going to circle that. That's what we're trying to find when the stick of dynamite explodes. Okay, so what do we do to solve this? Well, I'm trying to find the number of moles of gas, and here are a bunch of gases that are produced in the reaction. And so working backwards, those gases come from the nitroglycerin exploding, and we have to sort of realize that dynamite is only partially nitroglycerin, so only part of it is nitroglycerin. And so we're going to have to take that into account. And then, of course, we have the stoichiometry of the reaction, and we have to tie these things together. So often one of the problems is, how do we start? Do we start with the 40% dynamite? Do we start with the dimensions of the stick, etc.? And my usual advice is, if we have a number of different values, try to pick the thing that seems kind of most central and that's just an amount, not a conversion factor, because you'll use a conversion factor in the problem. And sometimes this is a little bit trial and error, but on this one, it looks to me like the mass that we have of the dynamite is probably the place to start. And I'm going to then say I've got 188 grams of, now I'm going to label things. I have dynamite, and just for ease, I'm going to have an abbreviation for dynamite, DYNA, and then I'm going to say, how can I convert from the dynamite into something that's going to ultimately get me to where I want to go, the number of moles of gas. And that's going to have to come from the nitroglycerin, so somehow I have to convert from dynamite to nitroglycerin. Well, what I know about the dynamite is that it is 40% nitroglycerin by mass, and 40% means 40 parts out of 100. So if I have 100 grams of dynamite, only 40 of those grams are going to be nitroglycerin. So again, I'm going to use an abbreviation. I'll use the abbreviation nitro for nitroglycerin, and I will probably have to use its formula at some point. And then I note that converts grams of dynamite into grams of nitroglycerin. And once you've done that, you should be able to say, oh wow, there is my nitroglycerin. I know its formula, so it's pretty easy to convert the grams of nitroglycerin into the moles of nitroglycerin, because that is going to be, we always want to go to moles because chemical reactions occur on a mole-to-mole basis. I'll let you do that part of it, but the number of grams of nitroglycerin you should be able to get. That's the molar mass, which of course comes from the formula C3H5N3O9. That should be easy enough to do. That will then convert grams of nitroglycerin into moles of nitroglycerin. And then, I obscured it just a little bit here, but we want to get to the moles of gas, and notice N2CO, H2O, and O2 are all gases, so I can convert moles of nitroglycerin into moles of gas by noting that for every 4 moles of nitroglycerin that react, we produce 6 moles of this gas, N2, 12 moles of CO, 10 moles of H2O, and 7 moles of O2. So you'll have to do the tough math. What is 6 plus 12 plus 10 plus 7? And that is the total number of moles of gas. So maybe I'll put that as a little side note here. 6 plus 12 plus 10 plus 7. So that's your number of moles of gas. And wow, let's see what happened. Moles of nitroglycerin cancels out, and this will then give us some number of moles of gas. And holy cow, I think that means we are done with the problem. Quick things to note, we never ended up using the dimensions, 20 centimeters long, 3 centimeters diameter. That might have been useful in some other kind of problem, but it's not necessary for this one. Okay, and the second question we're going to look at is question 8. And again, this one may have different versions, but they'll be similar in concept. So this one has a certain serving of chem cola that has a certain amount of phosphorus in it, which is in the phosphoric acid in the chem cola. And we're being asked the amount, the volume, of a certain concentration of sodium hydroxide that's needed to neutralize the phosphoric acid in the chem cola. All right, well, we need to visualize what's going on here, and sometimes it helps to draw a little picture. You might be able to do this in your head, but I'm going to just kind of make a little schematic visualization. And what we have here is some sodium hydroxide solution that is being added to some cola that contains phosphoric acid. And the reaction is going to take place, and it's going to be important to note what that reaction is, and then once we note that, hopefully that'll help us figuring out what's going on. So what ends up happening, we have phosphoric acid, H3PO4, and when we add sodium hydroxide to that, we hopefully recognize that we've got an acid, phosphoric acid, and a base, sodium hydroxide, and when they react, the hydrogen from the acid will combine with the hydroxide from the base, and that makes water. And then the sodium ion, which I should note is Na+, from the base, potentially combines with the phosphate ion, PO43-, from the acid, and that makes the salt. And balancing charge, this would be then Na3PO4. And so that's the unbalanced chemical equation. And then we hopefully are going to note if you have Na, only 1 on the left and 3 on the right, we're going to have to balance that with a 3. And then we're going to have 3 hydrogen ions reacting with 3 hydroxide ions to make 3 water molecules. And so our overall balanced chemical equation now is going to be H3PO4 plus 3 NaOH makes Na3PO4 plus 3H2O, and the acid, H3PO4, is neutralized by the base NaOH. And the stoichiometry, 3-to-1 stoichiometry, is going to be important. Okay, so that's going to be important information. The previous question, we were given the reaction equation. This one, we had to figure out the reaction equation. And now, again, we're given some information. Size of the serving of chem cola, the number of grams of phosphorus in the phosphoric acid, and then we're trying to find the volume of this sodium hydroxide solution. So here's what we want to get to. We want to find that volume. And what that means is we're going to need to start with the chem cola. And the question becomes, do we start with a 240 milliliter serving? Do we start with 39 grams of phosphorus? You know, what's our sort of starting point? And, you know, again, sort of different ways one could start. Sometimes you start one way, you realize you hit a dead end, and you have to try again. So some of it's a little bit of informed insight. But the serving, 240 milliliters, doesn't really tell me much or convert anything else. It's more critical to know the amount of phosphorus which is in the phosphoric acid. So my starting point on this one would be, I would say, okay, I've got 39 milligrams of phosphorus. And then that's in the phosphoric acid, and the reaction is phosphoric acid with sodium hydroxide, so I'm probably going to have to convert phosphorus to phosphoric acid, which means I probably have to convert milligrams. There's 1,000 milligrams in a gram of phosphoric acid. Sorry, of just phosphorus, so milligrams converted to grams. And then, let's see, what am I going to have to do next? I'm going to need to get from grams to moles for the reaction, and I'm going to need to get from grams to moles for the phosphorus. So use the periodic table, figure out how many grams of phosphorus there are in 1 mole of phosphorus. So make a little side note, periodic table, whatever that number is. And then that will convert grams of phosphorus into moles of phosphorus. And then what I really need is the phosphoric acid, but notice there's 1 phosphorus in 1 H3PO4, so I know that there is 1 mole of the element phosphorus in 1 mole of the compound phosphoric acid, H3PO4, and so that converts from moles of phosphorus into moles of H3PO4. And then it's going to be a long conversion, so I'm just going to kind of continue extending this conversion, and I'm going to need to convert from, so here we have moles of phosphoric acid, which we have. I need to convert from moles of phosphoric acid into, and let's look at, what are we trying to get to again? Oh yeah, volume of NaOH. And the reaction says for every 1 mole of H3PO4, we need 3 moles of NaOH. So for every 1 mole of H3PO4, we need 3 moles of NaOH. And so that converts from moles of H3PO4 into moles of NaOH. And then, let's see, we need the volume of NaOH solution, but we know the molarity. So a molarity of 0.125 molar is 0.125 moles of NaOH solution per 1 liter of NaOH. I'll put AQ there for solution, NaOH AQ, to distinguish from just the compound NaOH. So moles of NaOH in a liter of aqueous solution. And then, let's see, oh, we're almost done. Volume, we just need to be in milliliters, not liters, so that should be easy. 1 liter of aqueous NaOH per 1,000 milliliters of aqueous NaOH. And that converts from liters into milliliters. And sorry, we got a little bit squeezed there, but that then whatever number we get, converting liters into milliliters, whatever number we get for milliliters of NaOH solution, that's going to be our answer. And let's see, quick side notes. I think we went through everything, but quick side note here. This is the molarity of 0.125 molar is 0.125 moles per liter. And notice we use that conversion factor sort of quote-unquote upside down. Okay, so that is it. And hopefully that helps with the general thought process involved and how to solve these types of questions.